Well, good evening and thanks for coming. I've got a small audience here and a much larger audience out there. My name is Mike Wilson. I'm the Executive Director of AIA East Bay. And tonight we have Bob Hemphill from Aquatech to talk to you about low slope roof and severe weather. Did I get it right? There's another piece there too.
No, that's all right.
Okay.
It'll work.
Well, without further ado, will you take questions during the event or do you want to?
Prefer them afterwards because I'll probably cover whatever questions they have during the presentation.
Very good. So put your questions into the chat box. For those in the room, you can simply raise your hand. Bob?
Okay. How do I advance the slides?
Just say next slide, please.
Okay. Hello, everybody. Thanks for attending. My presentation is designing low slope roofing to avoid roof collapse for severe rain events and future climate changes. Next slide, please. There. This is just a few of my accreditations I've achieved through my short lifetime. One thing that to note is on the bottom there, there's a list for California contractor state license. I got my contractor's license back in 1981. And I'm probably one of the few people that you ever met that has actually installed roof drainage on a building before. So I speak from a little bit of expertise. And that's all the different accreditations I have. I'm also allied AIA East Bay member for years, right, Mike? Okay. Next, please. There's the next slide is showing a weather event in Houston, Hurricane Harvey. And the reason why I'm showing this slide is because some of this presentation will be focusing on Houston as an example of code requirements and stuff. I presented this talk similar at an event in Houston back in March, and I decided to keep the slides relating to Houston itself. I don't need to tell you that, Mike, is the next one advanced? I just don't know if I'm, okay. Number 4? Okay. Number 4 shows you a roof collapse that happened in Illinois this year. One person died and 26 people, 40 people, depending on what you read in the internet, were injured in this particular event. It was a concert, some kind of metal concert itself. 260 people were there. Could have been a lot worse. And I'm hoping that at the end of this presentation, you can decide how or learn how to actually avoid some of these catastrophes. The next slide shows a roof in Fort Lauderdale, Florida, that collapsed. Don't know the specifics as far as how many people were injured or anybody in the building itself. But again, an illustration that roof collapses are happening all over. The next slide, Mike, are they still on? The next slide is showing a local event where a roof collapsed in San Ramon on December 27th of last year. And the next slide after that is a roof collapse for a building in Oakland that happened on March 10th of this year. These local events I'm going to highlight because I think with a better design, we probably could have avoided these roof collapses. Great. To summarize, I think there's a big problem with the local California building codes as they're written. One, they don't really size roofing drainage for severe rain events. The way the roof drains sizing are done right now is that you take a severe rain event for 60 minutes, supposed to expect a steady rain for 60 minutes, and that event takes place once out of 100 years. I think that rain events are becoming more and more severe, more and more frequent. I know that you've experiencing some of the weather issues that are out there right now. The primary drains are primary scuppers. If you have a primary scupper that experience a severe rain event, that primary scupper will actually take the rain off the roof along with the secondary roof scupper. These two drainage systems will allow water to exit a roof under a severe rain event. However, if the primary scupper is blocked up or doesn't function, you're only depending on the secondary roof scupper to perform. And that becomes a problem because instead of having a safeguard, now you're depending on one secondary roof scupper itself to take water off the roof. The other part of the code is problem with the code is that they don't define what a conspicuous location or for roof discharge, roof drainage is, and that becomes a problem. And you're going to see this in the slide. It's particularly poignant in that there was a roof collapse event where one person died, where if the overflow drain had been located in a conspicuous location, that life may have been saved. The learning objectives, I'm not going to read them for you. You can actually see them on the slide. I can go one by one through them, but you can see actually what we're going to talk about. I'll cover them each one individually. And we're going to start with the learning objective number one is how to size roof drainage. This next series of slides will actually show you how roof drainage size is done. Problem with the current codes is throughout the United States, there's a lot of different states that use different codes. We in California use the Uniform Plumbing Code for roof drain sizing. There's other parts of the country that use the International Plumbing Code for sizing. And New Jersey actually uses their own particular code. And there's states and cities that actually mix up different parts of the code. So it's really, you're going to see a stark contrast of what the problems are with different codes. Going further to, we're going to talk about actually how to size. Oh, great. How to actually size roof drains themselves. According to the International Plumbing Code, which we don't use here in California, you take the roof area, the square footage of the flat roof area, and you add all the walls into the equation, 1/2 of the square footage of all the walls to determine what the size of the roof area that you need to drain. And this is probably pretty simple. You take the roof, you take all the walls, you add all the square footage of all the walls in this particular case, add that to the roof area, and that's the actual size of the roof that you have to drain, and that's how you have to size it. The problem is when you have the UPC is what we use, it's a different set of parameters. The UPC breaks it down into a lot of different categories, and we'll go over these, so I don't need to have to actually read this slide, but you'll see what I'm talking about and the differences between the UPC and the IPC, why some parts of the country go with the IPC and why we go with the UPC. I don't understand it. To me, the UPC is a better code provision itself. But for the UPC, you just basically take the roof area and you add 50% of a wall area itself. This is similar to the IPC. They add 50% of all wall areas. But the UPC is a little bit different. Uniform Plumbing Code, if you have two walls that are across from each other, they basically cancel out. The theory with the UPC is that the rain direction is in one direction. So one wall blocks the rain, another wall collects the rain. The net effect is zero. They also, for adjacent walls, the UPC defines the roof drainage sizing requirement is that you take 35% of one wall area, 35% of the second wall area, and you add that to the roof area, and that's the actual roof drainage area that you have to account for. The theory on this one is that roof 1 and roof 2 will block each other somewhat, so there's not as much rain. There's not 50% rain as with a single wall. You take a situation like there, we have a roof 1 and you have a roof area number 2. We both know they cancel each other out. James is going to tell us what 2B is. What would you add to the calculations of that roof area for wall area number 2B? We know that these cancel out because they're across from each other. 2B is going to be 50%. James is right. Yeah, thanks for listening, James. That's really good. In case like this, we know 1A and 2B are going to be 35% of the wall area. Robert, what's 1B going to be? Say 50%. It's right. It's right there at 50%. All right. All right. You're learning how to do sizing of roof drains. All right, Frank, 1 and 3, we know cancel out. This is according to the UPC. It's not the IPC. What's the roof area requirement for 2? Oh, shoot, Frank, listen. All right. Excellent, Frank. You can see how it gets more and more intricate, but it's really not complicated when you break down. We know that 1 and 3A are going to be 50% each. We know 2A is going to be 50%. 2B, James, is going to be 35%. He said it right. 3B is 35% because they're adjacent walls. 2A is 50. All right. Here's a all right, this one advanced. We all know that because the walls are across from each other, they're zeroed out, and roof area 2B, James, is 50%. They're not adjacent. 50%. Side by side. 50% of wall area 2B. Here's another roof area. We know all these. James, now you got this one. Yeah, 35%. Okay. Another scenario, we know we have all the zeros at the bottom because they're all across from each other. 2A and 2B are going to be 35%. And Robert, what's going to be 2C? 50. Robert says 50%. There you go. 50%. All right. Problem with the UPC, it doesn't jive with the IPC, International Plumbing Code. Remember, some states are following the UPC, some states are following the IPC. IPC, getting back, 1/2 of all the vertical walls. So in a particular case like this, IPC is saying 50% of all these walls are added to the roof area. And the UPC, again, it's different from the IPC. They eliminate all these walls on the bottom. You've got 35%, 35%, 50%. The UPC, to me, is a more thoughtful code than the IPC, but you can see that there's probably a universal or statewide issue as far as what this square footage of a roof area that needs to be drained. IPC, we know in this particular case, Frank, how much do we add for all these walls? 0, Frank. Oh, for the IPC, sorry, Frank, you're right. For the IPC, 50%. For the UPC, what do we add? Excellent. Whew, sorry about that, Frank. I take that back. No, I do. Don't add. All right. I apologized. All right. Getting back to the UPC, we're going to talk more about them specifically because that's what we use in California. You take the roof area plus the wall area calculations, which you all learned how to do. You take the rainfall rate and the amount of inches for 60 minutes, and I'm going to show you more about that. You have to convert that to gallons per minute. These formulas are, there's a constant that 0.0104. This constant, this is not really that important to remember. It's nice to know how the roof areas are actually calculated, including walls. But most of the time on a project, the structural engineer is going to calculate the rain requirements, or the plumbing engineer itself. But just to show you that the California Building Code, the roof drainage is based on Appendix D in the actual plumbing code itself. You have to refer to the plumbing code. You have to convert the roof area to gallons per minute. And that tells you what the actual, oh, I went backwards, my bad. All right, it jumped ahead. UPC, Uniform Plumbing Code, Appendix D in the code itself. It tells you what the rainfall rate is for 60 minutes and a 100-year interval. And it says 4.6. I'm going to compare this with San Francisco. So that's why I'm showing you Houston. The National Oceanic and Atmospheric Administration has a better chart. Instead of doing every 60 minutes, they can break it down to 60-minute times, or they can break it down to 15 minutes or 30 minutes. There's a lot of different information they've calculated instead of just the Appendix D with 60 minutes. When you have Houston saying that for 60 minutes, 4.86 inches per that hour of time is what you're going to get. If you had a sudden rain event and you had 30 minutes that deposited 3.54 inches and you added another 15 minutes, and for 15 minutes, there was no rain whatsoever, you're still above that 4.86. This code is inadequate for Houston. And what Houston did was very smart, is that they had made an amendment to their actual code. And they just said that for all primary roof drainage, all roof drainages, we're going to assume 8 inches per hour. Now, here's a case where San Francisco, where we are, the UPC appendix, oh, we lost the D, but it says 1.5 inches. You go to the National Oceanic Atmospheric, you break that down. Let's say it's not for, rain doesn't fall constantly at the same rate for 60 minutes. Rain falls at different rates. For 60 minutes, according to the NOAA, it's 1.29. You go for 15 minutes, they say it's 0.668. 30 minutes, 0.915. So if you took a rainfall for an hour and for 30 minutes it fell at 0.915, and you take a 15-minute that added on to that, and you can see that it's already above 0.15, above what San Francisco thinks is going to be 1.29. San Francisco is also a little bit strange in it, and it's the only city that I know of that actually mandates that you take the storm water and tie it into the sewer system itself. If anybody knows another city out there that does this, I don't know about it, but it's a strange thing about San Francisco. It's actually in their local building code. You take the rainwater, storm water, and you tie it into the sewer system itself. Our learning objective number 2 is going to be on external drains. I broke it down to primary, secondary, collector heads, and downspouts. All parts of drains that are external to a building that are piped to the outside. And this is my first question I want to ask Robert. Can you explain this picture? Can you explain to me what's going on here? Okay, what I'm looking at is I see a scupper down low, which normally would be an overflow scupper. I see a collector head up high. So I don't even know why the collector head's there. If that area gets wet, it's coming out of the actual. If that area gets wet, that scupper is going to see the drainage. Why they have a collector head tying into the downspout, it's strange. Here's another one that's hard to explain. Frank, if you can help me with this one, I appreciate it. Why these downspouts are ran this way, I don't know. Oh,
It's an artistic touch.
okay. All right, getting back to the California Building Code, we're going to talk about primary scuppers. One, they're required for entrapped water. Anytime you have a wall that can collect water, you have to have a secondary. There's no ifs, ands, or buts about it. It's just very clear that any area wall that can trap water, you have to have a secondary, a way of getting water off that roof in case the primary is blocked. Another code requirement is, this is going to sound really strange between the two, but scuppers, California Plumbing Code demands that the scupper opening be at least 4 inches minimum. That means height times width. It's got to be at least a 4x4. Doesn't matter what. However, you talked about the California Building Code. They say that the scupper has to be no less than 4 inches tall. They don't talk about the width. Why? Why one has 4 inches minimum width times length, and one has just the height? I don't know, but that's okay. We're talking about the secondary scuppers. There's some code requirements: 2 inches minimum, but the primary must be independent, not required for re-roofs yet. Just to show you that secondary roof drains must be at least 2 inches above the primary drain. Don't know exactly why this 2-inch requirement was made. I have a couple of theories. Is one, if the primary is blocked up, you have debris down low, at least your secondary is up a little higher, so maybe that debris is not blocking the secondary. The other one is that secondary has to be independent of the primary, and a 2-inch height requirement actually moves it away from the primary a little bit. That's the only reason I can find for this particular code requirement, but it's there. The other part of it, California independent primary of roof drainage. The secondary system has to be independent of the primary, so it's got to be separate. And the other thing is, this actually code requirement is changing. Next code cycle, all re-roofs are going to require a secondary roof drain. It's just going to be automatic. But now, currently, if a roofer goes up there and re-roofs a building and it has only one primary drain, they don't have to add a secondary scupper by code. Okay, now we're going to get into a lot of stuff that I actually see out in the field. Part of my job at Aquatech is actually to observe different roof installations. And this one I took a look at, and I wanted to ask James, what do you see as the problem here in this particular photo?
The tape measure appears very dirty, so it's hard to read.
That's one. We fixed that.
it's-
We got a better one.
It's less than 4 inches high.
Excellent. You're paying attention. No, excellent. You see that scupper opening is actually only 2 inches. This particular roofing contractor had all these overflow scuppers made for this particular project, and he made them all wrong. They don't meet code. It has to be at least 4 inches minimum. And you can see in this particular scupper opening, it's another job in Tracy that I was on where the scupper opening is less than 4 inches. It's got to be at least 4 inches tall and 4 inches wide if you go with the plumbing code. All right, job in Oakland I was on. Here's an outside wall. You've got in the center, you've got a primary scupper. On the right and left-hand side, you have secondary scuppers. It all looks pretty good until you get into the interior of the wall and you look at it. There's the primaries in the middle. The secondaries are on the side. I threw a tape on measure on it. The primary is 24 inches across. That's a nice size. It's a big building. But the secondaries are only 8 inches wide. So you basically have two secondaries that are 8 inches wide, 16 inches, trying to make up for a 24-inch primary scupper. This could be a problem. And here's a particular case. I saw a job in Oakland, and Robert, can you tell me what's wrong with this photo?
It looks like they're routing a pipe through the scupper.
It's not only a pipe, it's an electrical pipe. It's an electrical pipe conduit going through okay. I don't know the logic on this, but this is what we see out there. All right. Short story. AI East Bay. They have tours of different projects done by architects. In this particular one, it's a new building. I went on this tour. I was looking at this, and the first thing I say is, okay, what's missing in this photograph? Frank.
I see two problems. One, I don't see an overflow. And the likelihood of that downspout being the right size isn't
Okay,
real.
Frank is right on. He says it's missing an overflow. Remember, you got to have a separate overflow for a particular drain. We're not going to get into downspout size because I didn't actually measure this on a tour, but I'm focusing on more that you notice that there's not a secondary overflow scupper in this particular picture. Now, I've heard this argument before, and I've seen this detail before, where an architect will draw this collector head and they'll put a circle or a hole, an outlet in the actual collector head, which on the surface, they tell you, that architect will tell you, well, this is an overflow. It's effective in case there's a lot of rain. It can actually drain out of the overflow. But I always ask this question. What happens if that scupper is clogged up? That hole on the outside of that scupper doesn't do any good. You need a secondary scupper independent of the primary scupper. And these scuppers will clog up and they will back up. In this particular case, on a new building, and the reason why we know it's a new building, if you look at the windows, you can see all those stickers on the window. So somehow this architect missed it, or the third-party consultant missed it, but it needs a separate overflow because when you get into this, it becomes a problem. It doesn't matter about that hole on the outside. Another job, another architectural, AI East Bay architectural tour that I took. Here's a case where, again, a new building, and I'm looking at this and I'm saying, okay, where's the overflow? I thought I would be polite. So I sent an email to the actual architectural firm, the guy that was doing the tour. And I said, you know, by the way, I'm just concerned that there doesn't seem to be an overflow on this particular project. I'm looking at this particular building. It looks like you have a primary scupper only. Well, the architect was very nice. He wrote back and said, well, in this particular case, the overflow is stacked right on top of the primary. So what you're looking at is the primary. The overflow is actually, the actual primary is unseen. It's going into that collector head. But remember the rule, 2 inches minimum. It can be more than 2 inches if it's engineered. But if the primary scupper is 4 inches tall, minimum, remember, James, it's got to be, that's 4 inches of water that's going onto that roof. Anyway, not done correctly. Oh my God, another job in Oakland. No, this was actually in Berkeley. It's right around the corner. You can see that there's a scupper at the bottom. It's rectangular. There's a round circle at top. That's the overflow pipe. Remember, when you're sizing drainage, if you have a hole, a drain that's draining from the vertical, the water can get completely around the hole and drain down. If you have a hole that's on a wall like this, the water that's supposed to drain out is only going to drain out at the bottom of the hole. The overflow on this particular case is not done right. It doesn't allow the water any water that gets backed up onto this roof to drain out fast enough. The actual overflow, a round circle translates to the circumference of an actual pipe. It should be whatever pipe size is required. You need to times that by pi to actually get what the actual surface area, linear surface area of a drainage. And we'll get into a little bit more in that when we go a little bit further along. But showing you what I actually saw on the job site or this project site, you see the overflows in a round circle, the scupper's a rectangular object. What's worse is they actually took a downspout and they ran it in the middle a downspout from the roof below and they blocked off some of the drainage. This is not the way to do it. All right, collector heads. We're going to talk about a little bit about collector heads. This one is actually kind of a nice job in a way. They're recycling building materials. They took a paint can and they made it into a collector head. A lot of problems with this, but it's ingenious. It's not the correct way of doing a collector head, and we're going to talk about that in a second. Collector heads. Collector head in this particular case, what the contractor did is they took a collector head, they cut out the back side of it, they fastened it to the wall. The issue with this particular application is when that actual downspout or collector head backs up, that water is now against the wall. Has that waterproofing the wall been sealed correctly? Is there a collar on the backside of that scupper? I don't know, but I bet you it's not. It's a potential leak source directing water into the wall. Here's another case where they took a perfectly good collector head. Looks really well made. They cut the back out of it to mount it against the wall. This is a horror story in a project in Oakland I was on doing window testing. They have a collector head that's really mounted up high, right. And I get this point a lot where somebody says, well, maybe they want to just hide the primary scupper. And I always point, well, how are they going to hide the overflow? Anyway, so they hid the primary scupper. They ran the collector head up too high. They cut the back of it. And what happened was it started to leak. And I know it's hard to see, but at the wall, not between the leader pipe and the collector head, but the wall itself, it started to leak. It's draining a part of a green roof. That's why you see that green stuff there. Hit a control joint on the stucco, ran across. One thing I want you to look at is down below. This building is like 80 feet up in the air in Oakland. Somebody's got this horrendous looking thing, new building going on because one, the collector head is too high. They did it wrong. I went out there 6 months later, just to I was out there again doing testing, and this is what it looks like. Can you imagine having a building like this, a new building, 80 feet up in the air, and you've got this stuff going on? Downspouts get clogged. Here's an example. This is actually outside of our warehouse in Novato. This is a downspout that got hit by a car or hit by something, but they actually ran an electrical cable up through the downspout, helping to clog this particular downspout. If a downspout gets clogged up or the collector head backs up, the collector head in this particular case can direct 5 inches of water back onto that roof. Whether that roof is engineered to take 5 inches of water, I don't know, but this is a poor design. Here's another one, same job site where they took the primary scupper, they ran it outside the wall, but they ran it too long. They ran it so it's almost at the backside of that collector head. That thing will collect debris. That's going to back up over time. Oh no, it's got to play. Mike, what's going on here? Are they seeing that? What are they seeing? Okay, maybe. All right. I hope this plays. This is a key. Collector heads, downspouts, they can clog up. Oh no, it didn't play. I'm sorry about this, guys. It's really a great visual. This actual raccoon crawls down a collector head for some reason. And it's just to illustrate that collector heads can clog up. And it's supposed to play as a video. Don't know why. Any reason, Mike? It played in the office today. I checked. I made sure it played. Anyway, just to show you that there's a raccoon that's actually crawls down the collector head. Collector heads can back up. Learning objective number 3, we're going to talk about internal drains. Internal drains are roof drains that are piped from the interior to the exterior, and they consist of a primary drain, an overflow drain, and the dreaded sump pit. This particular case, this is a typical drain and overflow detail that we see at Aquatech. We take this detail and we exit. No good. We don't like it. One, a sump pit that it's draining into collects debris and water and becomes a blockage point. So we always prefer a detail where the drain and overflow are the water's directed through a taper system to them instead of a sump. We always prefer a direct. In Aquatech, we draw up a drain and overflow detail like this to show the components of the actual drain. If you ever see this detail or it's in your library or you're using it, get rid of it. Use this, and I'll tell you why. Oh, one other point is there's a code requirement. Roof drains shall have dome strainers. Unless it's a flat roof deck, then you can have a flat strainer. And this is a picture of an actual roof drain, overflow drain. You can see that there's a ring all the way around that's blocking that overflow grate. That grate, and that's the 2 inches that's required. But why we hate sump pits and why we X them out. This is an example of a sump pit that was done. It's actually done pretty well. It's a PVC membrane. It's all been detailed. Detailing is pretty nice on this particular project, but a sump pit requires a lot of different components. I'm going to take you one by one through them. You have a sump pit construction. Some contractors got to actually build a recess into the roof area itself. And this is a case where the sump pit construction is taken. In order to detail this correctly, you have to put a field membrane on top of the roof deck itself. You have to put a field membrane at the bottom of the sump pit. You have to build up the walls. Each one of these components are taking a roofer time and trouble to put together. A lot of welds that actually have to be done. You build the walls, then you have to do an outside corner on the top. You have to do an inside corner on the top. All these 6 steps cost a roofer money and time and trouble to build a sump pit that we shouldn't be using at all. Sump pits collect debris. That's just what they do. They're flat at the bottom. They don't direct the water off. You get accumulation of stuff. Smarter way of doing it is always to use a taper drain system. There's a lot of different ways of doing it with tapering the ISO. In this particular case, they even actually make ISO with a taper system to the drain itself. We think it's a lot better detail. This is a job in San Jose, a Hilton hotel, where they use the roof and overflow drain, but it doesn't have a sump pit. Everything directs it water to it. A lot less time and trouble for a roofing contractor. The roofing contractor, all he has to do is put the membrane into the drain bowl itself, seal it, clamp it, and then he's done. He's not doing all this welding. Okay, we're getting towards the end here. What time do we have, James? Okay, we're doing it right. We're probably going to finish a little bit early. That's okay. We're going to talk about best practices. This is what we at Aquatech always recommend. And I'm going to go step by step. We always recommend the addition of a secondary scupper on re-roofs. We know that this code change is coming, but we've always been recommending that if you have a re-roof and it doesn't have a secondary scupper, add one. This is going to change. So it's not a big deal. This is actually the code requirement right now that is going to change. You can see that recovering doesn't require a secondary drain yet. We also believe in locating overflow piping in a conspicuous location. This is where we get into the tragic part of the presentation. I'll explain why. The code says, doesn't define conspicuous location. All it says, in a location observable by the building occupants or maintenance personnel. What that means, nobody defines it, but we will, what we recommend at Aquatech. And the problem with this, there's actually an exception to the code right now where you can take the overflow or secondary drainage and tie it into the primary downstream of the last primary roof drain. Whether you can see whether the primary drain is blocked up with this particular code requirement or code exception, we think this is a bad idea. They should take this out of the code. And trying to explain this a little bit further, job in Oakland, roof drain and overflow pipe. You can see that there's at the bottom of the photo, there's some new concrete that's been put there. That's where the primary drain is draining out. That pipe on the wall is actually the secondary overflow. It's in a conspicuous location. Whether it can be observed by roof maintenance personnel or anybody else, I don't know. You certainly could trip on it, but that's a conspicuous location. But we don't think that's the best way of doing it. Getting back to this tragedy, Pete's Coffee Warehouse, 31023. I live in Oakland. I can tell you for a fact it was raining cats and dogs that night. At 3:30 in the morning, there was a man that was killed. He was in the Pete's office warehouse. The roof collapsed. Fortunately, somewhat, is that the next shift of workers was supposed to start in another half an hour. There could have been a lot more fatalities, but this could have been avoided if we followed putting an overflow pipe in a conspicuous location. And I drove to the site. Again, I live in Oakland, so it wasn't far away. And here's the actual picture of it, the collapse itself. Here's the problem. These are two pipes. One's the overflow and one is the primary drain. Which one's which? Now, James, I know what you're thinking. You're thinking, okay, they got the splash blocks. The splash blocks probably tell you that the primary drain is on the right. But if you're 3:30 in the morning, you go into work, it's raining cats and dogs, and water's only coming out of the overflow, not the main drain. You're thinking everything is normal. It's not a big deal. There's a chance that if you had known that the primary drain was blocked up and water was only coming out of the overflow, you may not have gone into that building. You may have called somebody to say, hey, you got a problem up there on the roof. The main drain is blocked. It's water's coming out of the overflow. In this particular case, here is the collapse. If you look at it, from you in the audience, it's hard to see, but there's a sump pit there. And there's an overflow ring that tells you that the overflow ring tells you that the overflow was on the left-hand side coming down the wall. I just think that this tragedy could have been avoided if that overflow had been in a conspicuous location. Now, show you in a conspicuous location. Here's a building, the building in the center. You're supposed to tell me where is the overflow. And I'm sorry, I can't ask the audience because you can't see it that well. But here's a particular case where the overflow is right above a window, way up high. Now, if this primary drain was blocked up and water was coming out of this overflow, it's 3 stories up. There's probably somebody on the street that might have noticed it. Whether they would have paid any attention to it, I don't know. But a fire department or a police department coming by, they might have said, hey, you got a problem. So locate that overflow in a conspicuous location. I don't care if people get wet. We want to save lives. We don't want the roof to collapse. We want people to know that there's a problem. All right, another best practice. Double the size of the secondary scupper or add another secondary. Easy. This is done well. You can see there's a primary drain is in the middle with the downspout, and on both sides, there's actually overflow scuppers. Twice the size or the same size, but it basically doubles the size of the primary scupper itself. And just a simple detail that everybody should out there be thinking about is trying to double the size of the overflow scupper itself. Remember, if a severe rain event happens and water is coming down, overwhelming the primary, the secondary kicks in, at least you're getting water off the roof. If the primary is backed up, then you're only depending on a secondary alone. So double the secondary. Here's a particular case. Frank took this photo. This is a Home Depot out in Tracy. What they did instead is they have the primary. The primary is on the left-hand side. The secondary is but they doubled the size of the primary. In this particular case, the one negative I have is the overflow or the secondary scupper is not 2 inches above, but the idea of increasing the size of it to get water off the roof is great. And this example of a drawing of a doubling up the size of a secondary scupper, just making it longer. Okay. You're going to say, okay, how much is it going to cost to actually do this? I went to a manufacturer that makes overflow scuppers with skirts, and I just got some pricing. One scupper that's 4 feet by 10 inches by 18 inches long costs $56.58. Remember, a 3-inch drain, a round drain, is going to require a minimum scupper of 9.43 inches, 3 times pi, 3.14. That's the actual size requirement to get for an overflow scupper. To add another scupper would cost $56.58. Times that by 10 different drains, you're talking about $560. Yes, it costs money for labor to cut a hole in that parapet wall, but that's a pretty cheap price. But it's even more economical if you just make the secondary scupper twice as wide, make it 20 inches wide. It's only $4 more than the actual primary itself. So we recommend doubling the size of the overflow scupper. Another one we're going to talk about is the Big 5 Sporting Goods in San Ramon on December 27th. At night, nobody was in the store. The roof collapsed. The fire department and everybody says it's because it was a severe rain event. What was more tragic is the actual roof collapse took down the mechanical sprinkler line, which also flooded the store. The good thing is nobody was in the store at that particular time. And I went to the actual site just to take a look at it and find out what's going on. You can see on the upper left-hand side, there's an overflow scupper. The door has a tag on it. The tag is unsafe to occupy. Looking at it, it has a 4-inch drain, cast iron drain. It's got an overflow on top. We already saw that 4-inch cast iron drain. So the question is, how big or wide should that scupper, overflow scupper, have been to service something that's taking a 4-inch drain? James. Oh, see, you're good. Look at that. 12.56. Nice. In this particular case, the overflow scupper, remember, it's a block wall, 16 inches wide. It turns out the overflow scupper was only 8 inches. It was undersized for the particular drain that was supposed to service. It should have been at least 12 and a half inches wide. Anyway, whether that added to the collapse, I don't know, but we can do better as designers. Another one is increase the pipe size of the overflow drain. This one's pretty simple, and eliminate that darn sump pit. Get rid of that sump pit. Here's a particular case where we took a 3-inch primary drain. On the right-hand side is a 4-inch. We just increased the pipe by one size only. The advantage of this particular one pipe size increase, gallons per minute. A 3-inch pipe takes 92 gallons per minute off a roof. Increase it to 4-inch. You've actually doubled the amount of, you've actually doubled the size of the overflow. Instead of having 2 separate scuppers, you just increase the pipe size, one pipe size. And I know, Robert, you're going to say, okay, sounds like it's going to cost a lot of money. Well, I did the math. I took a 30-foot run of pipe, 3-inch pipe, and I calculated the actual cost of what it's going to be with fittings and couplings to make it 4 inches. If you take a 3-inch pipe, all these different components cost a plumbing contractor $578. If you make it 4 inches, it's $729. So for $150 more, you can increase the overflow size by one pipe size for $150. It's probably cheap insurance. We always recommend, we have a overflow and a primary internal drains, increase the pipe size of the overflow by one pipe size. It's cheap insurance. Okay, here's the other one. SMACNA details, NRCA. collector heads. You've all seen this in the conversation about these collector heads that have been butchered, cut in the back. They're not done right. There is a proper way of doing this detail that will save a lot of problems, a lot of aggravation. SMACNA, this is their particular detail for overflow. A collector head tied into a primary scupper drain. They always recommend that the collector head is 1 inch below the bottom of the primary scupper outlet, 1 inch below. A couple of reasons why. If the raccoon that went down the pipe that you didn't get the chance to see blocks up the collector head, or there's a collapsed at the bottom and there's electrical wire running up through there, it doesn't matter. The collector head's not going to be affected. That water's just going to run right off the roof. You don't depend on the collector head or the downspout. If it's blocked up, it doesn't affect it whatsoever. This is what SMACNA recommends. NRCA. This, I know you can't see it from the audience, but this detail's been in existence since 2007. Why are we letting contractors put collector heads to hide a primary scupper? Even though you can argue that you're trying to hide it and you got an overflow right next to it. These details should be followed. Aquatech, we take a little bit further. There's actually, we take a detail. We like the idea of the back part of the collector head to go up and intersect and engage with the actual drip in the hem of the primary scupper. This to me is a bulletproof detail. This is one that should be followed. But at a minimum, we designers, we should always be designing it with our collector heads 1 inch below the primary, bottom of the primary. Forget these holes that you put in the scuppers. The collector heads, they just don't work. All right, a couple more things. IPC has a requirement for material in the roof drain bowl itself that it's got to be removed. UPC doesn't. We think that UPC should adopt what IPC does. And here's a couple of examples. That roof membrane material inside that drain bowl is helping to block up that drain. We want that the drain bowl to be as open as possible to get the water off the roof as fast as possible. Here's a case where you can see the overflow drain is really blocked up by a membrane material. This should all be cut back. It should be not blocking the drain itself. The last wish list, and this gets to the end of this presentation, is, boy, I'd love to see if we can increase the slope of a roof from code requirement 1/4 inch per foot to 1/2 inch per foot. I know Frank and I both feel the same, that even if you have a 1/4 inch per foot, you're always going to have a low spot, some spot. Yes, it's going to cost more money, but it would be nice if the code adopted this and said, just say, no more 1/4 inch per foot. We need a 1/2 inch per foot. And that's about the end of my presentation. My job at Aquatech is to sell our services. We're a small outfit. We're only about 20 people. One of the things that we've suggested to the International Institute of Building Enclosure and Consultants, IBEC, is that they champion a cause where they locate the secondary scuppers to daylight at the highest possible elevation. We want people to know, walking by, that the primary drain is clogged up, and that's why the overflow is kicking out water. It should be at highs, observable as possible. It shouldn't be down low. That's what it actually would save piping. If you can take the overflow piping, instead of bringing it down to ground level, if you can bring it up high, it actually saves some money at the same time. We also think that we should be doubling the size of the secondary scuppers, or adding a secondary scupper, or doubling the size. Overflow piping, one pipe size. The collector head, we think that should conform to SMACNA and NRCA details. And when we're redlining projects out there doing peer review, this is what we do. For us, again, a small company, 20 people, we kind of do it all. We were actually on a job site where a large consulting company was doing the third-party observations, and there was another company that was hired to do this smoke testing on the vapor barrier down below, and we were hired to do the window testing. We could have done it all. One-stop shop. This is what we do. And Aquatech loves it when I go out there and do lunch and learns. If anybody out there in the audience wants a lunch and learn, all you have to do is email me, bob@noleak.com. It's a real simple email, bob@noleak.com. And we can talk about setting up a date to educate the rest of your team if you thought this presentation has some value. I encourage all levels of learning, the beginners of your team, please let me come out there and actually show them what we can do. All right. Now, the last slide is questions. Typically, I'll wait for questions from the audience if there are, but I wanted to ask Robert, this presentation, what'd you learn today?
I learned that parapet walls have to be part of the calculation for roof drainage.
Man's a smart man. IPC, all the walls, 50% of all the walls, UPC, break it down. All right, James, what'd you learn today? You must have learned
I
something.
learned that overflows have to be, well, there's some best practices around overflow scupper design, as well as that interesting notion of a round pipe translating to a linear dimension. So
The pipe size times pi, the diameter times
yeah,
pi.
I knew the equation, but I didn't realize that that was the requirement.
Yeah.
Round drain pipe to
Well,
a,
you're looking
an
at the big
overflow
picture is that getting water out of a round pipe on a mounted on a vertical wall, you're only getting water out of the bottom. And that's why you've got to expand it out and make it the actual circumference. Frank, I'm afraid you know all this stuff. And don't talk about down.
I learned what I missed on my peer review that you're reviewing on your desk is going to have on it. I missed the secondary drain outlets on the peer review that we're reviewing tomorrow morning.
Thank you. And I hope that you can share some of your vast wisdom with me. That's the end of my presentation. I don't have anything else. If there's any questions from the audience, I'm sure Mike will relay them. Inside the living area?
Yes.
Obviously, it's nice to get, I worry about any pipes leaking inside of a living area, but it can be done. It can be done well. It can be very successful. If you think about a water line that might be inside of a living area up in the ceiling, for example, it's under 60 pounds per square inch of pressure. And then you put a drain line that certainly doesn't have that amount of pressure in itself. It will work. I'm sorry about that raccoon. You guys had to see that. The raccoon actually got out, crawled down the collector head. It's part of the show. Mike, what else you have for me? Oh, come on, guy. Somebody has to ask a question. Is there anybody online? I mean, on virtual? Look us up. We need talent. James, you knew all this stuff, right? Really? So are you saying that if I came back here with another presentation, you would think about attending? Mike, write that down. Uh-oh. Which has less risk of leakage. Are they asking a material question? Well, Frank and I will have different opinions. My number one choice would be coal tar pitch. That's a 50-year roof, but it's nasty for the installer, for anybody else. Other than that, PVC.
1/2 inch per foot drainage. That'll leak the least, no matter what you put down.
Okay, I'm not buying that because you can put down bubble gum and that's not going to work. Oh, it's not a roof. I think the question was, what's the best roof system for a flat roof? And most people would agree that a coal tar pitch is probably the less problematic for a roof system itself. It can go 50 years. However, very few people do coal tar pitch. There's a lot of issues with it. For example, the slopes can't be 1/4 inch per foot because the coal tar pitch will flow off the roof. But it's a great roof system. It's just not used anymore. Other than that, I still think a PVC. And the logic is you have a water bottle. Your water bottle is not made out of built up roofing or asphalt, or it's not made out of TPO or foam or a coating. It's made out of a PVC. And if they're keeping water inside of a PVC, to me, that's the best roof system other than coal tar pitch. What else you got, Mike? What's the best option for residential flat roofs? This particular case, I would still recommend a PVC roof system. If somebody came to our firm and said, okay, I want to design a building that won't leak, we think that PVC is, another thing about PVC is that they're solar ready. It's one of the few systems out there that if you decide in the future you want to add solar to it, it doesn't compromise the integrity of the roof. A built-up roof system, a spray foam, a coating, all are problematic when you actually do any kind of alterations or additions. PVC. I don't like gravel on a roof, any kind of roof. One, there's areas of the country when it gets really windy, the gravel blows off. Actually, in Houston, Houston itself, they don't allow ballasted roofs anymore because when the big winds came up, that they would take those rocks or throw them against the windows of the neighboring buildings itself. Gravel on top of PVC, no, don't need it. Okay. What else you have for me, Mike? There's a question, I guess, from a gentleman asking about heat gain. I'm not quite sure about the origin of the question. For one, we know that white reflective roofs do emit the sun's heat better than a black roof. So if you're talking about heat, that's one. We at Aquatech, we also recommend at a minimum 2 inches of insulation for insulating the roof deck itself. But heat gain, again, a white membrane will help you with heat gain. A black membrane will attract heat. A white membrane will emit or shed heat. I don't know if that answered Craig's question. To me, overhang is protects part of the roof. Flashing it is not problematic, that can be done, but an overhang, it's almost like adding shade to a roof itself. More overhang, the better. Just have to be careful how it's actually integrated. What else you have for me, Mike? Again, Craig? Craig. It's a more of an important question than you think. Craig's asking about urban interface roofing materials. I think that's the basis of the question. And I've been a long proponent of PVC in this particular case, just because it doesn't promote a flame. There's been multiple instances where there's a fire, Santana Row burnt down, built up roof, caught on fire because of a welder. The ashes went to across the street to neighboring apartment buildings and caught their roofs on fire. PVC in a urban landscape is the best choice, just because it doesn't promote a flame, and that's your actually best defense on a urban interface area. PVC. TPO, we hear it's another single ply membrane. We hear stories all the time about, there's stories in Vegas about welders on a roof where they caught the TPO roof on fire. Remember, TPO is made with rubber. It burns like mad. The roof was destroyed because it just caught on fire and went right across, burnt up the whole roof system itself. Just doesn't happen with PVC. I'd love to see Craig take a piece of PVC membrane and try to light it on fire. It just won't light. No mas? We're disconnected? Okay. Goodbye, everybody. Thanks for attending. Remember, Bob at No Leak, if you want to bring me into your team.